Hi guys, in this new opportunity we are going to resolve this problem. We want to calculate the Hamiltonian governing the motion of the pendulum, and this pendulum, its point of suspension, is constrained to move on a parabola. So the first step we are going to take here is to see what are the coordinates of the mass along the x-axis and the y-axis respectively. For example, here we need to know what is the angle here that the string is making with the vertical line, or the z-axis. In this case is theta. Okay, so this is the point of suspension, the blue one, P, and the distance between the origin of coordinates and this point along, and the projection of the point P along the x-axis is x. Alright guys, this distance is x. Okay, now because of the geometry of the problem, we can see that this triangle has this side and this projection. You know that this is L cosine of theta. Alright, and this side is L sine of theta. Okay, so sorry, this is sine of theta, L sine of theta. This is the opposite side. Okay, so this distance between this point and this point, that is the projection of the mass point, of the position of the mass on the x-axis, is L sine of theta. Okay, all right, now working along the z-axis, we see this is the distance, this is the projection onto the z-axis of the mass position along the z-axis. All right, but we need to know what is the distance between the origin of coordinates and the point P along the z-axis. Okay, this distance between the origin of coordinates and the point P along the z-axis is z. All right, and the distance between the projection of the mass along the z-axis and the point P, because of the geometry of the problem with this triangle, this side is the adjacent side of the triangle, right? The red one is the adjacent side. So, and that side is L sine of theta. Sorry, sine L cosine of theta. Okay, so with that done, we can write the position of the mass along the x-axis and the z-axis respectively. So this is the position along the x-axis, all this distance, and the difference between the z and L cosine of theta is the position along the z-axis. Okay, the green one. So this is the position along the z-axis, and this is the position along the x-axis. So how do we write those? we write the position R between the origin of coordinates and the mass, this position R, the position R, as R is equal to x plus L sine of theta along the x direction plus z minus L cosine of theta along the z direction. All right, remember this position, this distance plus this one is the position along the x-axis, and this distance minus this one is this, and this is the position along the z-axis. Okay, well, so the position of the particle is this, where theta is the angle between the z-axis and the pendulum, string. All right, and according to the problem, the equation of the parabola is z equal ax squared, where a is a constant parameter, All right. Now we are going to calculate the velocity. Okay, remember the velocity is the derivative with respect to the time of the position. So the velocity is equal to the derivative of the position with respect to the time, and in this case is x dot plus, because L is constant, we don't derivate it, and the derivative of sine of theta is cosine of theta, and we apply the chain rule, so we get cosine of theta dot along the x-axis plus c dot, okay, we are gonna replace this c into this part. All right, so it takes this for a. Okay, we are gonna derivate it, so it's gonna be the derivative to x dot is the derivative of x squared with respect to time, plus the derivative of in this case, because it's the derivative of cosine, is minus sine, and minus times minus and minus is plus, so here is plus L sine of theta dot z along the z axis. Okay, well, so we have the velocity of the mass and the position. Okay, this is the position and this is the velocity of the mass. Okay guys, here for example, now I can calculate the kinetic energy. Do you remember that the kinetic energy is K of the mass is K is equal 1/2 of the mass multiplying the velocity square. Okay, and the velocity is the square of the norm of this expression of this vector. All right. So, but what is v squared? But what is v squared? V squared is the applying the square of a vector with two components. It would be dot x dot plus L cosine of theta dot squared plus 2ax x dot plus L sine of theta dot square. That is the velocity square. All right. So we need to work on this expression and to calculate the square of these binomial expressions. Okay. So we need to calculate this expression and this one too. And we use the by this expression, like you remember this, right? Because from the algebra we remember that. Give me a second here real quick. From the algebra we remember that a plus b squared is a squared plus b squared plus 2ab. All right. So this algebraic expression, we need to apply this to this one and this one. All right. Okay, guys. So in order to do that, we have to get v squared it's gonna be x dot squared plus L squared cosine square of theta dot square plus 2x dot L cosine of theta dot plus 4 a square x square s dot square plus L square sine square of theta dot square plus 4 a x s dot L sine of theta dot. So here this is the result of applying this theorem of the algebra of this into this formula. All right. So this is the result. Okay, guys. Now we have to simplify this expression because it's too long. So the simplification here, for example, we are gonna put these two terms together. This one with this one, okay? This one with this one, I know this one with this one, and this one with this one. Okay, so if we do that, we get v squared is equal to, okay, x dot square plus 4a square s square x dot square plus L square cosine square of theta dot square plus L square sine square of theta dot square plus 2x dot L cosine of theta dot plus 4ax x dot L sine of theta dot. Okay, guys, now I'm gonna take common factor out of these expressions. So in order to do that, we have to take this one out with this of the parentheses, so we get x dot square multiplying 1 plus 4a square s square. Okay, guys, here plus we take out of the parentheses the L square theta dot square and theta dot square, so we get L square theta dot square cosine square of theta plus sine square of theta plus, we take out of the parentheses here the common factor 2x dot L theta dot. Okay, so we get 2x dot L theta dot multiplying cosine of theta plus 2ax sine of theta. Okay, guys, all right, remember this is equal to 1, this trigonometric property, cosine squared of theta plus sine squared of theta is equal to 1, so we get v is equal to x squared multiplying 1 plus 4 a square s square plus L square theta dot square plus 2x dot L theta dot multiplying cosine of theta plus 2, oh sorry, I missed this theta here, plus 2ax sine of theta. So this is the velocity, guys, square. All right, so I'm gonna highlight it with yellow, or either yellow or green is fine. Here with yellow, this is the velocity. So guys, we have to be prepared because this video is gonna be a little bit long, because this is a long problem, this is a long solution. All right, well, now that we have this, we can write the kinetic energy down as something like this. The kinetic energy would be K equal to, we know that is one half of the mass multiplying the velocity square, so we get one half of the mass, but we got the velocity on this expression. Okay, this is the velocity, and we are replace the velocity into the formula of the kinetic energy to have the whole expression for it. So it's gonna be one half of the mass x dot square multiplying 1 plus 4 a squared x squared plus 1/2 of the mass L squared theta dot squared plus 1/2 of the mass 2x dot L theta dot multiplying cosine of theta plus 2ax sine of theta. Okay, guys, we are gonna call this equation number 1, the kinetic energy. We are gonna call it number 1 equation. Okay, guys, I'm gonna highlight it too. Number 1 equation. I'm sorry, I want to highlight it with yellow. All right, here we go. Number 1 equation. Okay, this is the kinetic energy. So now, because it's easy to see what the potential energy is, the potential energy of the problem, of the mass, sorry, it's easy to see what the potential energy is. If we come back to the figure, we can see that the distance between the origin of coordinates and the mass along the z-axis is this green one, right? So and we know that the distance is the position along the z-axis is this. All right, so the potential energy is gonna be V equal to mgz, but we know that z is equal to the position along the, not necessarily c, I don't want to confuse the expressions and the letters, let's call it h. So but we know that h is c minus L cosine of theta, but we know that c is a x squared L minus cosine of theta. All right, so we can write the potential energy as V is equal to mg a x squared minus L cosine of theta, and this is the potential energy of the mass in this case, and we call this equation number 2. I'm gonna highlight it too, and this is the potential energy. All right, well, now we can write the Lagrangian of the system for this problem. The Lagrangian of the system, we know that it's given by the Lagrangian. We know that the Lagrangian is given by L is equal to the kinetic energy minus the potential energy. Okay, usually books and literature, they show the expression like this, T minus B. All right, guys, so with this done, we can okay, guys, we can write the Lagrangian like T minus V, and with that said, we write the Lagrangian L. We know the potential, the kinetic and the potential energy already, so the Lagrangian is L is equal to t minus v, and this is 1/2 of the mass x dot square multiplying 1 plus 4a square x square plus 1/2 of the mass L square theta dot square plus m x dot L theta dot cosine of theta plus 2ax sine of theta minus mg ax square minus L cosine of theta. Okay, this is the Lagrangian of the system. We know is the difference between the the kinetic energy and potential energy. This is the Lagrangian of the system. Okay, with the Lagrangian, we now we are gonna do something here. This is a problem a little bit complicated, so we are gonna write the Lagrangian in this way. For example, if the Lagrangian is a function of a quadratic function of the generalized coordinates. In this case, if you see the generalized coordinates, we are gonna see that they are, in this case, x and theta. These are the generalized coordinates for this problem. All right, guys. So when the Lagrangian is a function or is a quadratic function of the generalized coordinates, it can be written like this. It can be written like L is equal to L0 of Qt where Q is the generalized coordinate and T is the time plus 1/2 of Qt a Q. We are gonna call this equation number 4. Okay, what is Q? In this case, Q is the generalized coordinates expressed as a vector. Okay, guys, so this is a single column matrix. Q is gonna be, in this case, a matrix. In this case, because we are gonna write Q in terms of the generalized coordinates, right? In this case, is this matrix x and theta. Okay, guys, x dot in this case and theta dot. All right, guys, so this is the we are gonna write Q in terms of the generalized velocities in this case, and Qt is the transpose of Q. So it's the transpose and is, in this case, the row matrix x dot theta dot. Okay, so L is L0 is minus the potential. All right, L0 is minus the potential energy of the system, in this case the potential energy. So with that said, we can write the Lagrangian like this. If we pay attention to this, we can write the Lagrangian like 1/2 of x dot theta dot this matrix here m 1 plus 4a squared x squared m L cosine of theta plus 2 8x sine of theta. Oh my gosh, give me a second here, guys. I'm gonna erase this. Okay, m L cosine of theta plus 2a x sine of theta sine of theta m L cosine of theta plus 2ax sine of theta, and this is ml, this term. This is the matrix, column matrix x dot theta dot. Okay, guys. Well, all right. So minus the potential energy, in this case m g a x squared minus L cosine of theta. Okay, guys, so this is the Lagrangian expressing as this form, okay, with L0 representing the potential energy and 1/2 of qt aq representing this first term, 1/2 of this row matrix with this matrix with this one, this multiplication. But if we perform or if we do this multiplication of this matrix oh, give me a second, guys, of this matrix with this vector and this one, we are gonna come back to this Lagrangian in this form. All right, so it's straightforward going from here it's straightforward going from here to here to the Lagrangian in this form. Okay, guys, so that's it. That's the Lagrangian. That's the way we want to write the Lagrangian down. Okay, guys, so I know it's a little bit, it could be a little bit confusing, but this is the way we want to write the Lagrangian, because it's easier writing the Lagrangian in this way, because this problem is too long. It's a little bit complicated because of the conditions that the problem has. It makes the solution too long and a little bit complicated. We will have too many terms and too many equations in the solution. So we are trying to get a way to do it in a short, do you know what I'm saying? A short way. It would be a short way to write the solution. Okay. And this formalism, yes, this formalism, what it does is trying to give us the solution in a short way. So, all right, now we are gonna call this equation number 5 equation. Okay, so now the Hamiltonian can be written in this formalism like this. H is equal to 1/2 of pt a minus 1 p. Okay, I forgot something. This is A. This matrix is A, okay? This I'm gonna highlight it with green. This matrix is A, okay guys? Is A. This matrix green is A. This vector is qt, and this vector is q, okay guys? And this is the potential energy. We know that already. So with this done, with this written, we can write the Hamiltonian like this: 1/2 of pt with these formulas, a minus 1 p plus b0. This would be the definition for the Hamiltonian in these formulas. So what is P? P is the column matrix Px P theta. Okay? Px P theta. We remember that we need to write the Hamiltonian in terms of the momentum, generalized momentum, and generalized coordinates. So because the Hamiltonian is a function of the generalized coordinates and generalized momentum, it's like the Lagrangian. Remember, we got the Lagrangian in terms of the generalized velocities and generalized positions, right? That's why we write this Lagrangian in this form, because it's a function of the generalized positions and generalized coordinates, and possibly a function of the time, when depending of the problem, right? Depending of what kind of potential energy we have, whatever. Here we have the Hamiltonian in terms of the generalized positions and generalized momenta. All right, so that's why we write this P as the column matrix like this, and PT would be the transpose of this matrix, so it would be Px P theta. Okay guys, so what is A? A is the inverse matrix of A1. A minus 1 is the inverse matrix of A. Alright guys, so if we remember, and if we have a matrix M, for example, M is this square matrix AB CD. So what is the inverse of this one? The inverse, it would be M minus 1 is equal to 1 dividing this prefactor would be AB minus BC, multiplying D minus B minus CA. This is the inverse of the matrix M. So it's straightforward to demonstrate that M multiplying M minus 1 is equal to 1. But we won't do that here, because there is too many things to do. So there are too many things to do, so we have no time to do that calculation, but this is straightforward to get it. Alright, so if we have this definition, right, of the inverse, this it holds that M multiplying M minus 1 is equal to 1, then we can see that looking at this matrix here and applying this applying this formula to on this definition and formula of the inverse of a matrix to this matrix, all right, to this one, to this matrix, all right, to the green one, we will get that A minus 1. We know that A is that matrix, right? Is 1, applying the definition, is 1 dividing m square L square 1 plus 4a square x square. So 1 here minus m square L square cosine of theta plus 2a x sine of theta square, multiplying the matrix, okay, multiplying this matrix, multiplying this term that I just wrote is multiplying this matrix m L square minus m L cosine of theta plus 2a x sine of theta. Okay, here is minus m L cosine of theta plus 2ax sine of theta multiplying m 1 plus 4a square x square. So this matrix is multiplying this prefactor. Because this term is too long, I'm gonna call this prefactor, I'm gonna call it 1 dividing delta. That way we save space when we are writing everything. So we know the matrix right now, okay? So because the Hamiltonian is H equal to 1/2 of pt a minus 1p plus b0, we can write the Hamiltonian in terms of the matrix and the potential energy as H equal 1/2 1 dividing 2 delta, right? Remember, all this is delta, okay guys? All this term is delta, okay? So we get 1 over 2 delta multiplying the transpose of the matrix, in this case px p theta, okay, multiplying the matrix, in this case we know the matrix is ml, the inverse, minus ml cosine of theta plus 2ax sine of theta. Okay, here is minus ml cosine of theta plus 2ax sine of theta, and here is m1 plus 4a square x square. Okay, this is, I'm multiplying this vector px p theta. Okay guys, plus the potential energy. The potential energy is mg ax squared minus L cosine of theta. So this is this Hamiltonian, guys. This is the Hamiltonian of the system. Okay? So now we need to compute this expression to write the Hamiltonian in a easiest way, in a way to calculate the Hamilton equations in an easier way. So we are gonna multiply this matrix with the matrix, right, with this column vector first. So we get doing that, we get h is equal to 1 dividing 2 delta px p theta. Okay, so we remember multiplying this. I'm gonna use the highlighter here. So this one times this one multiply plus this one with this one. Okay, so if we do that, we get ml px minus ml cosine of theta plus 2ax sine of theta p theta. Okay, guys, now we come back and we multiply this one yellow with this one plus this one multiplying this one, and we get here minus m l, okay, cosine of theta plus 2ax sine of theta px, all right, px plus m l 1 plus a squared x squared p theta. Okay, guys. Okay, I'm gonna erase this and write it again because I need to write it. Okay, to write it well, plus m l 1 plus 4 a square x square p theta. Okay, we have that matrix. Okay, plus ng a s square minus l cosine of theta. Okay, now we multiply this vector or this row matrix with this this matrix. Okay, and we know, you know, that we do this, we multiply this with this plus this one. Okay, the multiplication of this one with this one, the multiplication, we are gonna add it up with this one and this one, multiplicating them. So this is an operation between, you know, between vectors or matrix, in this case column matrix and a row matrix. So the result of this calculation is H. Okay, I'm gonna take this M is multiplying each of the terms in the matrix. So I'm gonna take common factor M out of the matrix. So I can do that because it's a constant and it's multiplying every term of the matrix. So I can write M and I can get rid of the M out of the matrix to delta. Okay, multiplying px, multiplying the first term, term is L. Actually, guys, I can take common factor out ML. Common factor ML, 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 and ML. So I took common factor ML out. Okay, so now I multiply px times all the term. It would be px squared minus cosine of theta plus 2ax sine of theta px p theta. Okay, multiplying p theta now with this, it would be minus okay, minus cosine of theta plus 2ax sine of theta px p theta. All right. Okay, plus 1 plus 4 a square x square p theta square plus the potential energy. You know, the potential energy is mg a s squared minus L cosine of theta. Okay, guys, this is the Hamiltonian. All right, so I'm gonna simplify this term, adding this term up with this one. We are gonna have the Hamiltonian shorter like this. H is equal to ml dividing 2 delta px squared minus 2 cosine of theta plus 2 ax sine of theta px p theta plus 1 more plus 4 a squared x squared p theta squared plus the potential energy mg a x minus L cosine of theta. Okay, guys, this is a Hamiltonian of the problem of the system. Sorry, this is the Hamiltonian of the system. All right. This is the Hamiltonian of the system. Okay. All right, now we can calculate the Hamilton equations of the system. The Hamilton equations are, we remember Hamilton equations are x dot equal to the h the px that is equal to ml dividing to delta. Okay, is the derivative of the Hamiltonian with respect px. So this is the derivative of this one. It would be 2 px. Okay, 2 px, the derivative with respect px of this one, it would be minus 2 cosine of theta plus 2ax sine of theta p theta. And this is the first Hamilton equation. All right, now we can and if we simplify these two with this, we have 2 delta px. Okay guys, and this would be this first equation. The second one would be theta dot. Theta dot, we know that is the h dp theta, and that is equal to ml divided into delta. Now we calculate the derivative. So the derivative with respect p theta of px is 0, right? With this, for this term, for the first one. For the second one, it would be minus 2 cosine of theta plus 2ax sine of theta p theta. Okay, sorry, px. All right guys, plus okay, the derivative of this term with respect p theta is 1 plus 4a squared x squared p theta. Okay guys, and this is this equation for theta dot. All right, now we calculate these equations. Px dot is equal to minus the h dx. Okay, and this is equal to, because it's too long, this part, sorry, I gonna write it like, I gonna indicate the equation, but I won't calculate the derivative because it's really long. So, but it's gonna be writing the equation in a short way. It's gonna be the derivative with respect x of 1/2 pt, because it's this is the Hamiltonian, a minus 1 p, you know, plus the derivative with respect x of the potential energy, in this case would be 2mg ax, and this is another equation. Okay, and the last equation would be p theta dot is minus the h d theta, and we do the same. We are gonna indicate the equation because it's too long, the solution, but indicating the equation, we would get the derivative with respect theta of the Hamiltonian, 1/2 of pt. We know what pt are, minus 1a minus 1 pt p, and the derivative with respect to theta of the potential energy would be mg minus mgl sine of theta. Okay guys, this is the solution of this problem. Thank you for watching and see you in the next video. Bye.